thanks for those of you who came and braved the transportation and everything. So it's a long title and sort of a vague title. Many of especially the stochastic forcing part is slightly vague because I want to cover many different situations. So today will be, as much as I can, I will try to make it kind of light on assumptions, and I'll have more examples to see the general idea, to see what's happening. And as Pierre-Louis said, the work will kind of span over much of what I did during my PhD studies up until pretty recently. So basically, there will be sort of two main classes of examples here. The first is where the stochastic forcing or the noise is multiplicative in some sense. And the second will be additive. So I'll have two different sorts of results for these. And of course, I'll explain what I mean by these, what these words will mean will be more clear. So let me just dive right in to the first kind of class of equations I want to look at. So as I said, these are all going to be Hamilton-Jacobi equations, so they'll be first order. And by the way, the applications I have in mind, or the one main application, I should say, are random interface motions. So in either case, I'm going to have equations that in one way or another will model some evolving interface that has some random oscillatory velocity, and I want to see some homogenization happening under certain scaling regimes. Okay, so in the first case, my equations will take this form. So it will be a Hamilton-Jacobi equation with both space and time dependence, which is very fast and oscillatory. And I also have a negative power of epsilon in front of the Hamiltonian. So basically what's going on here is I'm going to be considering Hamiltonians in this section whose expectation is 0. And so it's like I'm doing a scaling where I want to go for large times. Having seen that the expectation of h is 0, I want to see kind of the fluctuations of the solution for large times. So, by the way, I should say, in all of this, there will be always some hidden probability space whose dependence I'm going to suppress for most of the talk, just for convenience. There's an initial condition, which for me will just basically always be bounded, uniformly continuous. Bounded is sort of not completely necessary. If you like the whole time, you can think of it as being Lipschitz. Doesn't change anything, really. Right, so as I said, the scaling is such that U epsilon is sort of like, well, it sees this parabolic scaling. Of course, in kind of classical homogenization context for Hamilton-Jacobi equations, you would see a hyperbolic scaling. Namely, you would not see the t over epsilon squared here, you'd just see a single epsilon. But like I said, I want to look further under this assumption that the Hamiltonian is sort of on average 0. And of course, to see something interesting happen at all, I want some sort of mixing assumption on my space-time dependence. Which is, again, a very vague word. And like I said, I'm going to be light with assumptions. And we're going to see in certain examples what I will mean by this. And finally, I should also mention, it will be of interest for us to look at different levels of scaling in time. So in particular, I'm going to add a small parameter gamma here both here and here. So that in particular the scaling applies really only when gamma equals 1. But so there's two reasons I want to adjust the scaling in time for some applications. The first is that sort of maybe from a material sciences point of view, it's the space and time scaling are kind of two independent parameters in essence. So it's like there's some small scale in space that of interest, and some separate small scale in time that's of interest. And at some point, I'm going to be taking both of those parameters to 0 and seeing what's happening. The second reason, which is sort of related to that, is that sometimes those two independent parameters are actually not quite independent. They have to depend on each other in some way in order to have some results. And I'll show some evidence later to see why this is not completely, that this is not so artificial. In particular, I will sort of need the temporal oscillations to be mild in some sense with respect to the spatial oscillations, which will translate to having gamma being a smaller parameter, so having an upper bound for gamma. But I'll come to all of this later. Right. So my goal in this first portion of the talk is to find some limit for u epsilon, and the goal is that I would want to see two things happening. I want to see homogenization happening in space, so the spatial oscillations will average out, and the temporal oscillations, because they sped up time so much, I will expect to see some increasing stochasticity. So in particular, the temporal noise will become more and more white in time. So all of this will translate to having a limiting object that solves an SPDE of this form. Where h bar is so for some m, some integer m, which we'll have to figure out what it is, h bar is some deterministic object and spatially homogeneous, and b is a Brownian motion. So this is really white noise here with the same dimension. This is absurd. M-dimensional Brownian motion. And with the same initial condition. I'm not going to keep writing the same initial condition throughout the talk. And okay, so as was mentioned, this sort of SPDE needs to be interpreted in the stochastic viscosity solution sense, which I know has been talked about in this room quite a bit. So this will be with the theory of Lions-Suganides stochastic viscosity solutions, which, of course, the aspects of this theory and the well-posedness of the equation is a topic with which one can and has been done fill a whole course. So of course I'm not going to get completely into this. Suffice it to say that the main aspect that we should know about these equations is their stability under local uniform convergence, and especially stability with respect to the different data in the equation, the most notable one being this path. Of course, another name for these solutions are pathwise viscosity solutions, because I can define them path by path. So for every Brownian path, or indeed any fixed continuous path, there is a solution that I can come up with for this, and I can obtain it, for instance, as by approximating the path by smooth solutions and taking the limit of the classical viscosity solutions. So this has all been documented almost 20 years ago under sufficient conditions on h bar. Again, I want to be light on my assumptions. Anyway, so this is my goal, is to figure out when it is possible to have a limiting equation of this form, and what it looks like. Okay, so let's, before I even write down examples, let's sort of formally see what we would need to do to prove this, or to formally derive the limit. So first I need to make some sort of ansatz, which for me, so I'm not going to actually write an expansion here, but my ansatz here is that, well, there are two different limiting behaviors going on here. One is the whitening in time, and the other one is the averaging in space. And my first ansatz is going to be that the homogenization is happening much faster than the temporal oscillations. So much faster with respect to the oscillations in time. So in other words, homogenization in space happens first. Which, I'll write this down with symbols. This means that u epsilon will be approximated by some u bar epsilon, that still depends on epsilon, where the spatial oscillations have all been averaged out, but there's still the temporal oscillation. So basically what I'm doing is I'm treating, I will be treating the temporal, the time noise part as sort of a slow variable. So it's rather difficult at this general stage to even write down what equation u bar epsilon should solve. So for this, I'm going to need to put a few more restrictions on my h. And we'll see, with my examples, that this will give us a rich class of examples to work with, and with many different kinds of behavior that will come up. So the Hamiltonians that I want to look at for p, x, and t, gradients, and space and time, basically I'll take some linear combination of Hamiltonians with some coefficients that depend on time. By the way, this little m here is not the same as this big M here. And I'll get back to that. So these Hamiltonians, again, I'll be light with assumptions, but let me just, for simplicity, let me assume that I have periodicity in space. In principle, this could be generalized, but I think periodicity is much easier to talk about right now. Meanwhile, these CIs, I want to be approximations of white noise. And what I mean by that, so the most abstract assumption I can come up with that is that if I scale these terms, well, even before that, I want CI to be at least piecewise smooth. It's okay if they have jumps, because I can still interpret solutions of this equation. Just I solve the equation up until a jump, and then I solve it again from the next jump. That's not a problem. So I want these CIs to be piecewise smooth, but then also I want them to converge to white noise, in the sense that if I scale them with this white noise scaling, or Brownian scaling, or central limit scaling, whatever you want to call it, it will converge to formally something like dBi for some Brownian motion bi. And it sort of goes without saying, but I should write it, that the CIs should have mean 0. And the HIs here I'm going to be taking also deterministic, so you really see that this Hamiltonian has mean 0. And it seems as if when I look at the equation satisfied by u epsilon for this Hamiltonian, that I should indeed see some homogenization of these HIs, and I should see some white noise appearing. So a naive, guess would be that these all homogenize to some h bar i's for I from 1 to little m, and then these all converge to some Brownian motion, little m dimensional Brownian motion. But as I mentioned, this is not exactly what's going to happen, and I'll show some examples to see why. By the way, what time should I end at? It's 11:43. I'm not sure. I go until 12:20. Okay, good. Okay. Right. So So this is my setup, and now I want to see, how far I can take this. So like I said, let's go back to my ansatz that U epsilon is approximated by something where the spatial oscillations have all averaged out. Well, the most general thing I can say is that U bar epsilon will solve an equation like this. There'll be some H bar, which will depend on the gradients, not on space and not directly on time, except that it has to depend on this thing that I've called the slow variable. Which is my scaled noise. So this is the equation I'm looking at, and I insist that I can't say anything more general about the H bar at this stage because of the nonlinear nature of the equation. So where does this H bar come from, which depends on two variables? Basically, it comes from the literature on periodic homogenization of Hamilton-Jacobi equations. Because, like I said, if I freeze these Xi's, I pretend that they don't even depend on T, basically I can figure out what the homogenized equation should be by looking at the cell problem. By looking at this cell problem formally, assuming it is even well post. So the cell problem, what is it? It's basically an equation for some periodic function v, and I determine what this constant is on the right-hand side by, for every fixed p and xi, I should be able to find a unique constant, p, depending on p and xi, such that I can find a periodic solution, which of course will not be unique. The solution won't be unique. In fact, it won't even be unique up to additive constant. But the point is that the constant on the right-hand side is unique. If I put a different constant, there are no solutions. So let's pretend that I can solve this cell problem for now. And by the way, this comes from doing an expansion, an ansatz where you have an expansion in epsilon. And then the v is what we call a corrector. So this is my intermediate homogenized equation. So now the next question is whether there is a limit now as epsilon goes to 0. Now I don't have any spatial oscillations to deal with. That's the upside. The downside is that the dependence on the noise, the temporal noise, is very nonlinear. Because this is a nonlinear cell problem here. There is just no hope that the dependence of h bar on xi would be linear. It's just impossible. Now there's one thing you can say by the uniqueness of the constant. You can, if I multiply the cell problem by a positive constant on both sides, then you can actually see, if I put the positive constant in here, you can actually see that h bar is positively homogeneous in this xi variable. Positively homogeneous. So at least I can pull this power of epsilon out. Okay, that's one thing we can do. The second thing we can do is let's now restrict to having an initial condition, which is just affine. And then you can see what the solution is. It's just p dot x plus 1 over epsilon gamma. And I can do a change of variables. Minus. Now, the limiting behavior of this is much easier to deal with, depending on what assumptions I put on my approximate white noise. Now, there are many assumptions that will guarantee this kind of convergence. By the way, I should mention this is in law sense, in the sense of converging in distribution. And my solutions, by the way, I should mention, will be converging always in this talk locally uniformly, so in the topology of locally uniform convergence. And in this case, they will be converging in law. At times, I'll have convergence in distribution, in probability, sometimes even almost sure, but basically, the topology is always locally uniform convergence, so I won't keep writing that. Right, so like I said, there are many different classes of assumptions we can put on these fields C that will ensure that they mix enough and yield white noise. I'm not going to write down a very general assumption about the mixing rate because it will take some time. And also because the examples I will look at will be a little bit more particular. I will be restricting to having C's which are basically discrete. So what I want is my CIT to be equal to a random variable xi k if k is, if t is in this unit interval from k to k plus 1, where my xik's are independent. So it's independent, mean 0, and variance 1. So basically, what I have is like Donskoy's invariance principle. I have some scaled random walks, and they converge to a Brownian motion. All right, so if that's the case, if these are my noise things I'm dealing with, and let me even say they're identically distributed, so really IID, then what I can see is that U bar epsilon will converge to P dot X plus some variance that depends on P times a Brownian motion, and this is in distribution, where the variance is given by this quantity. Put a squared here. And this is just from the fact that what I have for my U bar epsilon is also a random walk, scaled random walk. Now, this is almost true. This would be true if I knew that if I took the expectation of H bar of x, so if I plug in this random variable x, this representative random variable x that has the same distribution as all these other x's, if I knew that this had expectation 0, right? Because if it didn't, then the scaling would yield some blow up, and you could actually exactly see by how much, by pulling it back, by multiplying by the right power of epsilon, and you'd see some average coming out. But if the average is 0, then this does hold. Now this is it's not too crazy to want this, given the structure of the cell problem. It seems somehow that the dependence on C, even though it's not linear, should in some way have this zero average property. It still won't always be the case because of the nonlinearity of the problem, which requires me to look at the theory of viscosity solutions, and we know that theory is not very amenable to multiplying by negative constants. Positive constants, sure, but negative constants, it's not so great. So that's the first problem, is that I don't know this. The other problem is we have to figure out what happens for arbitrary U naught. And this is not so obvious. This is not the type of problem where knowing what happens for affine data is enough to tell you what happens for any data. In particular, so you might see this and you might guess how do we know that the limiting equation in the end is not just having my h bar being exactly the sigma and having a one-dimensional Brownian motion. So in particular, big M would just be 1. Why is this not the case? So let me write it like this. Why not? I guess it would be minus, but of course, because it's Brownian motion, the law doesn't really matter. So why do I not have this limiting equation? So it will, necessarily, because of the way the central limit theorem works, it will necessarily be the case that if I look at the components of my resulting h bar, it will be the case that if I do this, I take the sum, j equals 1 to m, I should, of course, get sigma squared. If what I'm saying here and here is consistent. And so what this implies is that if I have a solution of this equation and a solution of that equation with affine initial data, the laws of the solution should be the same. But it will turn out that even if this holds, the law of this solution and the law of that solution for arbitrary initial data will not be the same in general. So we really do have to, it won't. There's no hope essentially of just knowing what happens for affine initial data and being able to use that information to say what happens for arbitrary initial data. There's no hope. So we have to go further, and basically we have to restrict our assumptions a little bit so we can see what happens in general. And so I'm going to do this again with some examples. So first let's look at the first example. The first one is extremely easy, actually. At least easy to say what happens. And that's when little m is equal to 1. So that's when my Hamiltonian is given by a single Hamiltonian times a single source of noise. And in that case, the cell problem, first of all, becomes not this infinite family of cell problems for different values of xi. Where's my cell problem? Here. But it just becomes 2 cell problems. So it becomes this one and this one. And I have to be careful now where I put my parentheses, because I'm being extremely pedantic about the fact that this is the cell problem and the effective Hamiltonian for h, and this is the effective Hamiltonian for negative h. And what we would like, of course, and this is the same as having, as saying that in the one-dimensional case that h bar in xi is completely homogeneous. What I would want to say is that minus h bar is equal to minus h bar. Because that would make this intermediate homogenized equation much easier to deal with, because it basically would say that I could take the xi completely outside and really have linear dependence on my noise. You should guess that this isn't such a straightforward question. The answer is yes, if h is convex in the gradient variable. So that's fine. But it's no in general. And there are actually examples that you can construct of non-convex Hamiltonians where this fails. Another way of writing this, by the way, is saying that h and the Hamiltonian created by putting a minus sign in front of the y, that these have the same h bar. So it's sort of like saying that again, this is the periodic case. It's sort of like saying that the orientation of the torus is irrelevant. So the orientation you pick for the torus is irrelevant for the dynamics. And so no in general means that the way that the spatial dependence is ordered actually makes a difference for the effective Hamiltonian. So I found this rather interesting, and this goes kind of down, a long rabbit hole of weak KAM theory and things like that, but I don't want to go there. But anyway, so what this tells me then is that if H is convex, I can actually say quite a lot, namely convex and coercive, then whenever I have this kind of equation, and let me make notation a little bit easier and put a C epsilon, then U epsilon will converge to U bar, where U bar solves this equation with just a single path and a single Hamiltonian. And this will happen for my C epsilon given by this, this scaled quantity here. Where do I have it? Right here. I guess this is C delta, but I'm plugging in delta equals epsilon to the gamma. But it will happen for any value of gamma. It will happen for any type of approximation of white noise. In fact, I can even weaken my assumptions on the H. I can have them be, I can add more scales in epsilon. I can make it almost periodic. I can make it stationary ergodic. So really, the one path case is much easier to deal with and very particular. And it really has to do with the structure of the equation, that somehow going backwards and forwards in time along these temporal oscillations, in the averaged, in the sense of when I average, they're not going to make a big difference, and I will be able to have in all cases, I will be able to have a limit. And it also has to do with the stability of these equations in this one path case. When I have a convex Hamiltonian, I actually have very strong stability in the path variable, which I had mentioned before, and it's a stability which is independent of the oscillations in space, and actually only sees the growth of the Hamiltonian. So this is very good for us for the homogenization purposes, because basically I don't have to worry about the limiting behavior of the path while I homogenize, and vice versa. They're happening completely independently. So the one path case is very, very good. And I'm probably going much slower than I thought, so let me see. No, I could do something. Everything changes when we go to multiple dimensions. So I should mention that effective Hamiltonian, in the case where I have one path, when little m equals 1, is just the same one that I get from the classical periodic homogenization theory, or the homogenization theory in the other context that I mentioned. It's just the same one, and it has nothing to do with the noise at all. So that is one aspect that will change in the multiple path case. The effective Hamiltonians that I get they will depend in some way on the law of Xi, on the law of my white noise approximation. So if I choose a different white noise approximation, I'll actually have a different equation completely. And even the law of the solutions will be different. So that's one main difference. Not just the nature of the effective Hamiltonians, but also their number. So this big M that I wrote somewhere up here, this big M, the number of Hamiltonians, the number of Brownian motions, will also depend on the law of the X's. So let me just do some examples now, because it's not worth writing some general assumptions. So m bigger than 1, what do we do? So here's my first example. Let me just take u epsilon t plus u epsilon x, absolute value. This is a very simple Hamiltonian. multiplied by 1 mixing field for white noise approximation. And then the spatial oscillations you'll see in this sort of potential term multiplied by a different approximation. So this is my equation. And you can actually, before I say that, so again, I'm going to be very particular now. I'm going to take the x's to be these discrete random walk type approximations of white noise. And I'm going to be even more precise. I want these x's, which are the increments of my random walk, to be of Rademacher type. So they're 1 or -1 with probability 1/2. So it's a simple random walk. So in that case, something very nice combinatorial happens, which is if I look at my effective Hamiltonian that I get from the, just applying the cell problem to this equation, it is some nonlinear function of xi, but where xi is in this very nice space. It can only be -1 or 1, pairs of numbers that are -1 or 1. And as such, it's a polynomial. And in fact, because I have, you'll note that, whatever, if I put 1 -1 here, it doesn't matter which one, I'll have a Hamiltonian which is either convex or concave. And so essentially, the remark what I have over there is true, that multiplying by -1 doesn't change anything with, or, it has this nice relationship, this consistency. And so therefore, I'm only going to see in my polynomial expansion, I'm only going to see 2 terms coming out. And of course, this is only true if I restrict to xi being in -1, 1 squared. Because it's just a linear algebra problem. It's just counting dimensions. And so this is very nice, because then I can very easily discover the limiting equation, because then I just use my stability of pathwise viscosity solutions again, and my limiting equation will just be this one. Actually, Brownian motions, right? So this is one case where my naive guess was right, that my little m and my big M will match. And in fact, in this case, you can exactly compute both of these, h bar 1 and h bar 2. H bar 1 will have a shape sort of like this. It will be flat. Then we'll have slope 1/2, and then we'll have slope 1. And the other Hamiltonian, h bar 2, will be flat, then have slope -1/2, and then be flat again. The places where the derivatives jump are the same, and they're determined by f, basically. They're determined by the max of f, the min of f, and the average of f. Those 3 parameters will shift this around. But you'll notice that the effective Hamiltonians depends, in some sense, on both the structure of this coefficient in front of xi1, and also on f. So somehow both of them together are determining both of the effective Hamiltonians. So now what happens if I take the exact same equation, but I add many more potential terms? So I'm increasing m from 2 to something larger, little m. So what happens if I take many more? Under the same assumption that I have this Rademacher type noise. Well, in that case, again, I'll have some polynomial expansion for my h bar in the noise term, if the noise only takes values in 1 and -1. But it's much more complicated now because m is much bigger. And it will have some large sum like this, where these indices, j is some multi-index, like this. So these are actually powers here. Or sorry, this is actually, I'm multiplying the different values of xi. And again, this is only when xi1 through xm take values in 1 and -1, which means that this product, of course, will only be 1 or -1. Moreover, for all these different multi-indices, as I range over them, I'll have this large family of independent Rademacher random variables again. They're independent because it's easy to compute that. So I have this large sum over multi-indices. By the way, they will all be odd, again, because I have this consistency where I can multiply by -1 in my cell problem. So I will never have an even product, even numbered product here. So actually, the number of multi-indices that I have is 2 to the m-1. And so that is actually the dimension of the Hamiltonian, the effective Hamiltonian in my limiting problem. I'll have some effective problem like this. I should say, so for some j from 1 to 2 to the m-1, I'll have something like this. And I'm not going to write the computations down. I keep mixing up the dimension. This is all in dimension 1. Although it can really be generalized to multiple dimensions. Just in dimension 1 was where I could do computations. And again, one can run computations, and it's very complicated because now the effective Hamiltonians will depend on all the different f's and how they interact with each other. But you can write down examples, and you can see that in general, you know, the extra Hamiltonians that you get will not cancel out. So you really will have more than little m effective Hamiltonians in your limiting equation. All right, so, and I should finally mention that, so these types of assumptions can be generalized to having all kinds of different Hamiltonians here, as long as it is true that whenever you put pluses or minus in front of them, you'll either have a convex coercive Hamiltonian or a concave coercive Hamiltonian. It's pretty easy to find many examples where that happens, for example, this one. Another type of example is when each of these is if I have all of my hi's being, say, 1 homogeneous in the gradient variable, in which case these, the resulting equations I have are level set equations, which means that the level sets of the solutions are, you know, model some interface motion. And this is the point I made at the beginning of the talk, that I could have, I could model some random interface motion and see how they homogenize, how their velocity homogenizes on large scales. And it's not too hard to write down assumptions on these velocities, these normal velocities AI, such that the cell problem is always well posed if you put whatever list of pluses and minuses. Okay, so before I get, you know, too far into other details and run out of time, I would finally like to go to the second part of the talk, which will have to be a little bit shorter. And these will be for problems that have additive noise structure. So, what time is it? Right, okay, I just have barely enough time. So let me write down the type of problem I can pose in this section. So here the nature of the equation will be a little bit different. In fact, it will already be a stochastic equation. But the solution theory is not quite so complicated as the ones we've already seen. So it'll be a Hamilton-Jacobi equation, very simple looking, except it will have some stochastic forcing on the right-hand side of this form. And again, with a fixed initial data, not depending on epsilon, bounded uniformly continuous. My H is going to be, basically I want it to be superlinear and convex. So for instance, H could be a quadratic Hamiltonian, in which case this type of equation is actually, there's a lot of interest in studying an equation like this with stochastic forcing. So it's like an Eikonal equation. It comes up in many, many different applications. One of them, for instance, is where the graph of the solution is some evolving interface that comes from like a turbulent combustion model. So this is like if you look at certain reaction diffusion equations and you look at the sharp interface limit, you might see the graph, it will look like the graph of the solution of an equation like this. And basically, there's some burnt region up here, if I take the turbulent combustion analogy, and there's an unburnt region here, and this interface is going this way based on the way the combustion reaction is happening. So there's this kind of spreading term that comes with the Hamiltonian, which there's all these generalized parabolas that are kind of pushing this down. And then there's also a very noisy term, which is adding some further complications. Which is based on the environment, and it's dynamic because I have this Brownian motion that is changing with time. So the question I want to pose here is, theta is just some fixed positive parameter. What happens when epsilon goes to 0? And the way it looks, a very naive answer would be that it would just converge to the solution of the same equation with 0 on the right-hand side because of this power of epsilon here. But otherwise I wouldn't be writing this down. The whole point is that the oscillations of f will play a very large role here, and we'll actually observe a sharp transition in my parameter theta of when that exactly happens, when the noise really vanishes. So how can we see this? Well, let's remember that we're interested in scaling limits, and these parameters will come out from certain scalings. So let's see the scaling that indeed will preserve the left-hand side of the equation, the hyperbolic scaling, which is the one we're used to if we're looking at homogenization of Hamilton-Jacobi equations. So if u epsilon is obtained in such a way by the scaling, then this function u, which I guess should also depend on epsilon, but I'm suppressing that for now, that will satisfy, if you go through all of the Brownian scaling, exactly this equation, where we no longer see any dependence on epsilon, apart from in the initial data, which now is very large and very slowly varying. And so the oscillations are happening on a so-called unit scale. We'll see no dependence on epsilon apart from what happens in front of the noise, which is that we'll see an extra power of 1/2 coming out. So from here you see exactly that theta equals 1/2 is extremely important. And what happens above and below it is, we should expect some change in behavior. And indeed, that's exactly true. So the first, I realize I haven't really been writing theorems down, mostly because it takes too long, but here's a theorem I can write down, which is that as epsilon goes to 0, by the way, I didn't write anything down about f. F here we could take to be periodic, but we can also, it's completely fine to have f be stationary and ergodic, some stationary and ergodic random field, but I do want it to be bounded in C1, independently of the probability of the probability space. So there's a deterministic constant C that bounds it globally in space-time in the probability space. So now the conclusion is that as epsilon goes to 0, U epsilon will converge to, it will converge to U, where U is in fact the solution of this equation with no noise, if theta is big enough that the oscillations of F play no role. And it will converge to negative infinity otherwise. Not otherwise, I'm sorry, if theta is less than 1/2. So if theta is too small, so if the amplitude of the noise is too large, then actually I'll have I'll have some explosion. So what that means from my point of view of the interface motion is that on large scales, the noise actually has an extreme enhancement effect on the velocity. Okay, so finally, I can ask the question in my remaining 5, 6-ish minutes. What happens for theta equals 1/2, which is the scaling critical case? Because this is already an interesting result. Just, the surprising, or a sort of surprising answer for theta less than 1/2 already gives us something. But I would like to know more. I would like to know what happens exactly at theta equals 1/2. And there, what we find at that level is that the scaling gives us exactly we actually get a homogenization problem. So what we get exactly is so in law, I should say this is also in law, this equality, because of my Brownian scaling. And this convergence is in probability. So in law, the equation that I have for U epsilon when theta equals 1/2 is this one. So what I have is a homogenization problem where I have a space-time environment where the dependence on the space-time parameter is stationary and ergodic. And that's true for F in space, and it's true for the white noise in time, because it's extremely ergodic and mixing. In fact, it's completely independent. And by the way, I should mention the F and the B I'm assuming to be independent. I don't want any correlation between them. They're basically on different probability spaces. And so it's a stochastic homogenization problem. So I can treat this with methods that we may already know. But it's a new problem because there are homogenization problems of this type, very general type, that have been treated by many authors. But this is a different one because my dependence on time is not only unbounded, but it's completely irregular. It's completely singular. It's not even well defined, a priori, in a pointwise way. Nevertheless, I can still solve this problem. I can show, in this case, that U epsilon will converge in probability to some U bar, which solves a homogenized equation. So it looks exactly like the same result for when theta is larger than 1/2, except that H bar need not be the same as H. And in fact, if F is any non-constant function, or a stationary ergodic field, so as soon as it's non-constant somewhere in the probability space, in space, and also in space, then H bar is actually larger than H everywhere. for all p. So that has to do with a few things. First, with the isotropy of the white noise in time. So even if f is non-constant in a certain direction, the white noise doesn't care, and it will sort of spread that information everywhere. So I could write it down mathematically with formulas, give you some intuition, but that would take some time. But it shouldn't be a surprise somehow, because the sort of the spreading that happens from the Hamiltonian part in the equation of my interface motion, basically what it's going to do is it's going to see the noise, and it's always going to kick it around somewhere else. The noise is never going to cause any cancellations. So the noise will have an averaging effect, but it will never completely cancel out because of how the h spreads this interface in a nonlinear way. So I will see some enhancement happen for my interface motion, but it will be finite enhancement. I can actually quantify it exactly with this h bar. So let me close by saying a few things about this problem, what makes it interesting. So the methods, like I said, are maybe classical is the wrong word, but they're standard by now in this context. I will I'll find some subadditive quantity associated with the problem. In this case, because h is convex, that's not an issue. And I will use the subadditive ergodic theorem. In this case, on this stationary and ergodic space-time environment. What I will also need, a very important tool in the analysis, I will need regularity of u epsilon. I will just need some kind of modulus of continuity for u epsilon, even local in space-time, that is uniform in epsilon, that doesn't depend on epsilon. And this is where things get very complicated. Because again, for such equations, this kind of regularity question has been studied. Whether one can find modulus of continuity for the viscosity solution that doesn't depend on the oscillations in space and time, which from the homogenization perspective is extremely important, something that only depends on the growth of the Hamiltonian in the gradient variable. Now, in my context, that would seem to suggest that I want something, I would want some regularity that only depends on the size of f, on the supernorm of f. However, to make sense of this equation, I really need f to have more information than just being bounded, because basically the very cheap way to make sense of this equation, cheap but effective, is to just subtract off the right multiple of Brownian motion, and I have to be careful now with my no, I'll write this. I have to be careful with my epsilons. If I subtract off this term from my u epsilon, this is exactly the term that causes the singular non-defined problem. And when I subtract it off, I discover that u epsilon tilde solves a classical equation. By classical, I mean there's no singular terms. It's a random, there's a random parameter in the equation, but there's nothing I need to define. Past the classical theory of viscosity solutions. And so now you say, okay, here's an equation which is classical. It looks like this equation here. Let me look up the available results on regularity of Hamilton-Jacobi equations. The problem is that if I try to apply them, I will have this term which is completely unbounded. There should be a gradient of f, of course. So the gradient of f naturally comes into play, and therefore I have a power of epsilon. Now the Brownian scaling helps you a little bit. Namely, if I replace this with t, then I can replace this with 1 over epsilon to the 1/2. But that still blows up, so it doesn't help you completely. And so what I was able to do then is obtain this kind of result. I was able to find that u epsilon, let me see. Let me pose it for this problem. So the problem is to have some kind of scale invariant regularity estimate for the solution of this equation. And what I was able to find is that I can find some alpha, some alpha modulus of continuity, so alpha Holder norm, which is bounded in the following sense. So the probability that it's larger than some constant plus some parameter lambda is bounded in some way by the sup norm of f, so that's good to see, to the power p divided by lambda to the p. So for any p, I can do this, and the constant here will depend on p. So this right away seems great, because it looks like I only see the sup norm of f and not its oscillations. So where then does the oscillations of f come in? So that will come in the dependence here for this constant. So this constant necessarily will depend on the C1 norm of f. However, it will depend on it in this way. So it will depend on f sup norm, but then also on this particular product, the product of sup norm of f with the gradient of f, sup norm. And now that is going to be a scale invariant quantity, because for this equation with epsilon, there's this epsilon to the 1/2 that comes out. And so this function here, epsilon to the 1/2 f, scaled by epsilon like this, x over epsilon, this product here, sup norm of f times the sup norm of df, is bounded independently of epsilon. In fact, that product looks a little bit like the C1/2 norm of f, the 1/2 Holder norm of f. It's a little bit bigger than it, or much bigger in the sense that they're not comparable in general, but it's related to it. So in fact, it's not completely the sup norm of f that's important, but really this product. And that product is scale invariant, and therefore I have scale invariant regularity, and that's an extremely important tool then in the homogenization proof. And indeed, one last thing I'll say is that if you look at this estimate, if I replace f with this epsilon to the 1/2 times f times x over, evaluated at x over epsilon, this will actually give me another power of epsilon coming out, which means that I'll be able to say more. I'll be able to use some Borel-Cantelli argument to say that for epsilon smaller than some random threshold, I actually have a uniform bound in the probability space for these alpha norms. Okay, so I think I've laid out plenty of examples now, so I'll stop. Thank you very much again.